Welcome back to Intro to Modern AI. Today we're going to finally start part 2 of the course where we're going to talk about large language models. Large language models do really form the basis. Large language models, I should say, and also extensions of these, like vision language models, etc., really do form the basis for most of the AI tools that we all typically use every day. And therefore, it's really good to sort of get a deep understanding of these models and how they work. And that's going to be the main point of this part of the course. Now, I do want to emphasize that language models that you interact with are not just language models. They're also extensively trained after just being a pure language model. But nonetheless, language models are kind of the technical core of a lot of what we're building in AI. And therefore, we're going to spend a lot of time covering this topic and kind of figuring out the details of how these things work. And in fact, throughout this course, you're going to build a large language model, train it really from scratch in the homeworks, and in doing so, you'll really gain a pretty deep understanding of the way these models actually work. Before diving into large language models, though, we're going to talk today a little bit more abstractly. We're going to use language modeling as the example, but we're going to talk a little bit more abstractly about the class of model that we're kind of moving towards in machine learning. And this is what I'm going to call a structured input model. All right, so I'll define what that means in a second, but as a general outline for this particular lecture, we're going to start off by talking about language modeling. I'm going to sort of come back to the example. We've been using the example of kind of classifying images for a while now, images of digits. I'm going to come back to the example of language modeling now, and this is really going to be the example we now switch to for most of the rest of this course. We will then talk about moving from unstructured inputs. This is how, for example, we represented images in the homework so far. This is a big vector of pixels that didn't really have any structure built in. So unstructured to structured inputs. And then I'm going to talk about the nature of really all models, all neural network models that process structured inputs. And in particular, this class has this common theme of elements of three. But I'm going to talk about the three elements, or the three operations, I should say, of structured input models. So these are models that take structured inputs and produce some output. Structured input models. And finally, I'll spend a very short amount of time just highlighting a few examples beyond text. So the running example here is going to be text. But I do want to emphasize that this basic idea doesn't just apply to text. It also applies to other sequence inputs. It also applies to images. It can apply to graphs. It can apply to really anything here. And I'm going to be very brief here because this course really is going to focus on language modeling from now on, but I just want to highlight this is a very generic, kind of general approach. All right, so let's jump into language modeling. And the first thing we're going to do is just kind of recap the basic goal of language modeling. So remember, in machine learning, you have an input and a desired output. And in the case of our images, that input was a image of a digit, and the output was the label of the digit itself. But in language modeling, our input, the way we typically think about this, is our input is some sequence of text, sort of an initial sequence of text. For example, the quick brown dog, the quick brown fox, messing up the order of that sentence, the quick brown fox. And the desired output would be the word jumps. Again, this is a common sentence. The quick brown fox jumps over the lazy dog. And this is sort of the input-output pairs we have. Now, that's not the only pair. We actually would have entirely other sentences where we have the initial part of the sentence, we're going to predict the next output. But also we would have sort of prefixes of the sentence. So we'd also have, the quick as a prefix and the desired output would be brown. And of course, there are other outputs we could have too. So we could also have an input, the quick, and the output would be maybe and, or something like this. And this is sort of how we set up the input desired output pairs for this problem. Now, we are going to talk about a classification task here. So just like before, the predicted outputs of the model are going to be probabilities that give an indication over what is the next word. What's the probability the next word is and, what's the probability the next word is brown, etc. But this is sort of how we set up our task. So but this is just sort of a conceptual. This is not an input to a machine learning model as it is right now, right? This is not really a mathematical representation. This is sort of more just the textual representation of our task itself. So I'm going to actually start with a simpler example. And just to highlight how we take kind of inputs like this and outputs like this and how we encode them in a machine learning setup. So I'm going to take a simpler example here. And the simpler example is one that just has a vocabulary that contains 3 different words. The words are going to be, there's letters in fact, but you can think of them as words. There's going to be the words A, B, and C. All right, so that's our entire vocabulary. Everything about every word in our language is going to be either just the word A, the word B, or the word C. Not a very interesting language, I know, but it's just for conceptual purposes. And so what we're going to do here is we're going to think about how, we're going to again think about an input. So let's think about an input that could be, for example, the phrase A, B, C. And let's think about an output that would, or a desired output, that would just be, let's say that if we see this phrase, ABC, we want to predict, in some sequence of text that the next word is A. All right, so this is a very sort of simple example. And the question is, how do we represent this as an input to a machine learning model? And the thing we're going to do is we're going to take each individual item, and really each individual item in the input here, and we're going to encode it in what's called a one-hot vector. All right, so we're going to encode this letter A here as the vector 1, 0, 0. And the idea here is that this position is the indicator that word is A. So this just sort of means that it's equal to A. If the second position was highlighted, that would mean this word was equal to B. I shouldn't use approximately equal there. I should use something like equivalent to the word A. This is equivalent to the word B, and this one here would be equivalent to the word C. All right, so that's how we represent that first letter A. Now, of course, the same thing happens here for the other letters in the sentence. So the next word would be represented as the vector 1, 0, 0, 1, 0, and the next would be represented as the vector 0, 0, 1. Okay. This, again, is what's known as a one-hot encoding. So these things here are called one-hot encodings. And they're sort of the obvious thing to do here. They're just sort of saying, we're just going to develop a vector that kind of represents which of these elements is actually at that position. And so these are sort of how we represent our inputs. The output here is, of course, it's just the letter A. So keeping kind of with our convention that inputs are vectors and outputs are just indices of what the desired output is. This desired output here, and I'll even call this Y. That'll just be in the set of 0, of 1, 2, and 3. And in this case, the A would just correspond to the number 1 here. It would be the first word in our vocabulary. Okay, so this is kind of conceptually how we represent these inputs here. But now I want to be a bit more specific, because previously so representing, I should say, the inputs. Previously, we always had it the case that our inputs x were always going to be a vector in Rn. And our outputs y were going to be some number from 1 to k, where here k is in fact the vocabulary size, because we're predicting a word in our vocabulary. But this was always our case. And so again, for the sentence A, B, C, there comes the question of how we should represent that. And just like with an image, we represent it by just taking all the pixels and stacking them into one great big vector. We could also think about representing our input as just a stacking of all the one-hot encodings. So in this case, what we would sort of do, and I'll write this in blue here because this is sort of more becoming more math. What we would do here is that we could represent x as the vector 1, 0, 0, because this part here, kind of annotate it, this part here represents the encoding of the letter A. It has a 1 in the first position. Then the next sort of group of 3 would be 0, 1, 0. This element here would represent the word B. And then finally 0, 0, 1. And this grouping here would represent the word C. And so in fact, this is what we would call kind of an unstructured way of representing our inputs, right? Because we take our entire input sequence and we just represent it as a great big vector that kind of represents our entire output. Of course, in this case, if our output was just the letter A, our output in that case would just be equal to 1, right? Because we were predicting the next word to be A. And this is, I should say, sort of output A corresponds to, let me write this a little bit cleaner here. In the same way as before, what we would say is that output A just corresponds to y equals 1. Okay, but it's also the case that there's going to be a bit of a kind of a breakdown here. If we represent everything like this, we don't actually have that much representational power. And for all sorts of reasons, well, I shouldn't say that, but of course these are sort of in some sense mathematically equivalent. But what we're going to do here is we're going to take a slightly more structured approach to representing our inputs. Because this really, and I should maybe even highlight this more, this is an unstructured approach that represents our inputs as a vector, one big vector. What we are going to do instead, really in the rest of this course, is think about single inputs not as single vectors, but actually as matrices that start to capture some of the structure of that input. So let me say what I mean by this. I want to say that we're now moving to structured inputs. Which we're going to represent as matrices. And in fact, actually, I'm going to maybe start this new section here rather than do it here, because I want to sort of get this in some detail. But what we're going to do in this for the rest of this class here is move from, as I was saying at the beginning, structured to unstructured. Unstructured to structured inputs. And again, maybe I'll just write this explicitly again, that we're going to move to structured inputs as matrices. Okay, so what is the basic idea here? The idea here is we're going to take our previous input, which we sort of thought as a vector in Rn. Again, this is the stacking of all the one-hot encodings of our input, a stacking of all the pixels in the image, etc. And we're going to think about representing this a bit more naturally in terms of a set or even a sequence of elements. And so we're going to move from representing these things as just inputs in Rn to instead matrices, which are going to be a big X. I apologize again for the fact that big X's and small x's look very similar in my handwriting. Hopefully it'll be clear which one we mean. But we're going to think about representing these things as matrices, which we will denote in general as being in T by D dimensional. I'm going to use D here as my sort of dimension that I typically have for the number of columns in the matrix, and T is the number of rows. I don't want to focus too much on sort of the details here, right? So obviously, if you could just stack the elements in each row together and get a big vector, but it's actually going to be very important to think about each individual input as a matrix, and so we're going to do this for now. I also want to emphasize that this is not just, in general, this is not just the initial inputs to the model, but also internal representations. So remember, in a neural network, we sort of referred to the internal hidden layers or activations, whatever, as representations or internal terms we compute in the neural network. And in general, just for simplicity, I'm going to kind of use this term X here as a matrix to represent not just the initial input to the model, but also kind of each individual or potentially each individual internal representation as well. And depending on usage, this could be the input to one kind of layer, or the very initial input of our model. You have to kind of just glean that from the usage that I have, but this is going to be the basic setting here. Okay. Now, again, this doesn't seem on its own that sort of big a change. And in fact, we've already seen this, right? We've already seen this, and I'll just sort of say, as an aside here, I'm just gonna recall mini batch examples, right? We already had matrices, mini batch examples, or mini batch inputs. We already had matrices where we would take, a big matrix X and store the individual elements as the rows in this thing. And we called this a matrix that was typically B by N. Again, I don't want to focus too much on the indices here, but here B was the number of elements in our batch, and the number of rows was the number of inputs. The important thing that I'm trying to emphasize, that I need to emphasize here, is that this whole matrix no longer represents a batch of examples, sort of an independent grouping of examples. We will, in fact, use tensors that have another dimension on the front that sort of captures the batch size. But each matrix here, you should think of it as capturing kind of a single example, right? And so the important thing about this representation is that we're going to use it to store more structure in our inputs. We're going to somehow have our inputs not just be a great big list of everything, but it's going to be essentially a set of different elements that describe different aspects of the input. So let me just, of course, go back to my example of return to the example of our input being the word ABC, and our output being just the letter A. Well, our output doesn't change here. We still have, y just equal to I shouldn't say a set there, the number 1. But now I'm going to represent this thing here as a big matrix X. And actually, I apologize here. I realize that I have 3 elements and 3 rows. Maybe I will actually, just for the sake of this example, add another element here in my example, just so it's clear sort of which is the length dimension and which is the one-hot encoding dimension. So I'm actually going to consider this example with 4 elements in my input sequence. In this case, X here would be an element. Well, I'll actually write it down first what the size is. It would be a matrix which is 4 by 3 because there's 4 elements in my sequence, and each of those has 3 dimensions because we use this 3-dimensional one-hot encoding to represent each element. And so in fact, this particular example would be the matrix 1, 0, 0 that represents the letter A here as the first element. Then the next element would be 0, 1, 0. That represents the letter B. And similarly, 0, 0, 1, which represents the letter C. And in this case, with one more example, it would be 1, 0, 0, which represents the letter A again. Now, it is important to emphasize that we could just stack these whole things together, right? I could stack this row and this row and this row and this row all in a great big column, and that would be an unstructured representation of my input. And of course, any operation you apply to this thing, you could also apply to that, right? You could, of course, do kind of any manipulation you would do in this matrix, you could also do on the vector. But the point is that even though these two things are equivalent, it is very useful to think of more structured and really, I would say, sort of modern models, modern machine learning models, as operating directly on this matrix of inputs, on this structured collection of inputs. All right, and in fact, and this is sort of not an exaggeration, and I will kind of emphasize this point many times during the course, really every real modern network doesn't work like the simple neural networks you've built so far. They really work like elements that process these sorts of structured inputs to form outputs. Now, in the next few classes, we're actually going to move from predicting kind of just one output of these models to maybe predicting multiple outputs. But this is much more sort of a detail about the models themselves. For now, conceptually, you can think of them just as processing groups of inputs, and the output can be, or sets of inputs, or collections of inputs, and the output can be whatever you want. All right, so what this means here is that our machine learning model, our model H, is now going to be, actually let me write this again in blue. Actually, I write it down here. So our model now becomes not a function that maps just inputs to outputs, or inputs that are vectors to outputs, but inputs that are matrices to outputs. So our model would, for example, be a function h, which now maps t by d dimensional vectors to outputs 1 through k, and in fact, later on, or actually, sorry, it's vectors in RK, because we, again, still predicting probabilities, so vectors in RK. We will eventually move to even more structured outputs than that, but this would be one example of kind of what a machine learning model would now look like. Okay, so again, this is a seemingly a subtle shift, but from now on, we're going to use matrices instead of vectors to represent the inputs to our approach, or our models, and we want to emphasize this sort of shift we've made here. I will come back to actually the example of images in a second, because I want to cover some examples. Obviously, this is sort of a very natural representation maybe for sequences of text. A big matrix that has all these indicators of which things are what. But in general, I actually want to emphasize in this class, this particular lecture, that this same paradigm actually allows for many different types of inputs as well. Before I do so, though, I want to highlight the three operations that make up really all models that process structured inputs. And this is going to be important because really the way these models work, and this now applies to transformers, but it also applies to many other classes of models like recurrent neural networks or convolutional networks or graph neural networks. The way these models work is basically by applying three different classes of operations to this structured input representation. And I want to make the point here that, again, this is a little bit, there are some slight extensions of this, so there's slight ways in which we actually extend this, but the vast majority of modern AI methods should be viewed under exactly this lens of the three different operations of structured input models. And it's important to kind of conceptually understand what each of these is doing. All right, so let me just list these three elements here. Remember, we have our input, and this can be either the initial input to a model, or it can be an internal representation. And we're going to say that at all stages now, this is going to be a T by D matrix. We will, of course, there are ways of changing, modifying T or D in intermediate layers of a big network. D might change in intermediate layers from the input itself. But again, for simplicity, I'm just going to kind of think of our input or our internal representation as being this matrix X, which is T by D. Okay, so the first class of operation we have is right multiplications. And I'll even say right multiplications by W. And I'll further say that W would say be a D. I should say W. I should probably put something like, for example. Because of course the real E could be a different size. The real W could be a different size, but let's just assume for now that it's going to be D by D, i.e. it won't change the size. So what this looks like here is the multiplication X times W. Now, of course, this is, actually very similar to what we've already seen before, but I'm going to write this again. I'm going to use my my sort of way of writing matrix multiplication to write this in a particular way. I'm going to write this as, I'm going to write X by its different elements. So now, when we write X by its different elements here, these are no longer different examples in our training set. These things here, and I might even emphasize that a little bit more here, each row here is a different element of the input. Right? So the first might be the first word, the next might be the next word, but it, again, as a matrix, captures the different elements of our input, of our structured input. And I'm going to multiply this by W. And what this does is, again, just by our simple kind of matrix math here, is that it basically forms a new matrix where we multiply every row by W. And actually, you know what? I used the convention before that we multiply W transpose, so I'm going to put a W transpose there as the convention. It doesn't matter because it's still D by D, so it's actually fine to just use that convention. All the way down to XT transpose times W. Now, the key property of this, and this actually should look very familiar, because this is exactly how we applied a linear operation to our mini-batch matrix, right? This is exactly equivalent to the case where each individual row of X here was a different element in or different, example in a mini-batch, and this operation was exactly sort of the linear operation applied to that mini-batch. So in other words, what we're doing here is we're taking W and we're applying it as a linear matrix to each row of X. So applies W to each row of X independently. Whoops, I'm kind of overwriting myself there. Put another way, I'm going to keep writing those little implication arrows. There is no mixing mixing a bit more clearly. There's no mixing between elements. Right? This output here does not in any way, this first row of the output only depends on the first row of the input and W. It does not depend on the second row of the input. It does not depend on the last row of the input. It only depends on the first row of the input. That means that if you only apply, or whether when you apply right multiplications like this, there is no sharing of information between the different elements in our representation. All right, we are effectively treating these all as independent examples, and we are applying a linear transform to them. This is obviously not sufficient for things like text prediction, because if you look at this example, if you just multiply this matrix here by matrix on the right, you're applying, a bunch of matrices to this element, independently this element, and this element, and that is like trying to predict the output of, say, the next word using each word independently, right? Not using any structure or any coordination among the words. You're just treating each word as sort of an independent element. And that's not a very good way of sort of predicting these things. So that leads us to the next operation that we typically apply in structured models. And this next operation is left multiplications by some matrix. And again, I'll sort of say EG, because there are different ways you can do this. But you could do it by multiplying by a T by T matrix. And that would be, for example, the expression A times X. Now, I'm going to again write this out, but I'm going to write, rather than write it by sort of the rows of X, I'm going to write it by, at least initially, by the rows of A. So I'm going to write this expression by taking each row of A all the way up to A T transpose. These are just elements here of the matrix A. I'm going to multiply this by the whole matrix X. And what this gives, given a similar sort of way of writing matrix multiplication, is the whole first row of A times X. And then the next is the whole second row of A times X, etc. All the way down to A T transpose times X. And diving one bit deeper, in fact, let's look at this particular element, the first row of this output. Well, this thing, remember, A1 transpose times X, that is a linear combination of the rows of X according to the coefficients of A. So this thing in particular is equal to, it's a row vector here, and I'm actually going to maybe write this just to, I'm going to write this just to emphasize this thing as a row vector. This thing is equal to the sum, in this case from I equals 1 to t, of, well, it's all the elements of this particular vector here, and that would be the elements A row 1 column I times the vector xi transpose. Okay, so it's a linear combination of the elements of the rows of X with the coefficients given in A. And kind of the punchline here that I'm trying to emphasize through all of this is that now this row, unlike this case before, I'm going to switch back to the previous slide here, unlike the case before where this first row depended only on the first column of X, in this operation, this first row depends on all the rows of X, right? Because it sort of sums over every single row in X. And so what we're saying here is that a left multiplication mixes together the representations, I should say all the representations or at least it can mix together all the representations. Actually, you know what, I'm going to say mix together all the elements of X because I want to emphasize that it's mixing together the different elements. All the elements of X, i.e. all its rows. This is the operation that enables you to share information between the different internal representations for each element in your structured input. So again, going back to our example of representing text, if we had a sentence like this and we were only able to multiply on the right, we could never sort of capture anything about the order of these words, about the fact that there's a structure to the words, all this kind of stuff. We would just be operating on each individual word independently, and every time that same word occurred, we have to make the exact same prediction, or at least get the same representation. By using a technique, by using multiplications both on the left and on the right in our eventual neural network model, we are able to, in the case of left multiplications, mix together the different representations and therefore share information between all the rows of our matrix, between all the elements in our structured input. And these two operations kind of are the core ones that we use in modern AI models to actually capture kind of the full structure of these inputs. There are, of course, a few caveats of this, and the actual way we form these things can in fact be dependent upon the inputs in some sense. So there are ways that slightly kind of go beyond this basic paradigm, but conceptually, these two operations are extremely important and kind of the core operations in some sense of modern neural networks. They're also, by the way, by far the most computationally demanding aspects, and really the vast majority of time in these models is spent either performing left multiplications by our representations or right multiplications of our representations. And the very last element, again, these are neural networks here, so they aren't just linear models. So the last representation that we have there are nonlinear operations. And these, with few exceptions, but almost always, these are applied to rows of X, i.e. to each element. Kind of like the left multiplication or right multiplication multiplies or applies this linear operator to each row independently. These nonlinear operators also typically apply to each element independently. Again, with some slight additions we're going to have here in the precise nature, say, of self-attention, which we'll cover next time. But conceptually, again, this is how you should think of this. So these are things like applying, i.e., activations. So maybe you would activations in a neural network. You might have, the sigma x or something like this. Actually, let me write that as blue just to be consistent. Sigma x, where for sigma here just being some nonlinear function that maps real numbers to real numbers, and this is then applied element-wise. It also involves things like the softmax. So you could take the softmax of, say, rows of X and exponentiate them and divide by their sum. You can do all sorts of things like this in applying nonlinear operations, but they're typically, for the most part, applied to each row. And we'll cover some of these. But really the combination of these three things is really how all modern AI methods, all modern neural networks work at their core. And now, of course, the choice of what nonlinear operations you use, kind of how you form these mixing operations and everything like this, this is what's going to determine the actual structure of our networks, which W's you use and such like that. This is going to determine the actual structure of our matrix, of our neural network, of our model. But these are the basic operations, right? And by combining these three different operations in different types and very, very kind of minor modifications to these things, you basically get all modern AI models. Okay, before I move on, I just want to highlight the fact that although we are going to focus primarily on text for the rest of this course, this paradigm goes well beyond text, and it can actually capture very different examples as well. Things like images, things like sound, things like other sequences, things like graphs too, right? I actually will briefly give some detail on these things when it comes to images themselves, but really what I'm trying to highlight here is just the fact that this paradigm is very generic, very general, and really does apply not just to text, but really to kind of structured inputs in general. So for example, let's consider images. So an image, is a grid of pixels. So, okay, I'm going to one more time kind of draw my little cat here. So our image is a cat. We have our cat's eyes there, little nose and whiskers. All right, so we have our image of a cat here. And the way this is represented, the way we represented it before is, of course, a grid of pixels. I'm not drawing the pixels very finely here. These are, of course, too big, but that actually is very appropriate for what I'm about to do next. Before, we represented an image by taking kind of every single pixel value and just stacking it together in a great big vector. Now, you might think that the obvious way of representing this as a matrix was, in fact, as a 2D grid. And you could do that. That actually is a reasonable thing to do. But what's more common as a way of representing this as a structured input is to do what's called convert the image into patches. And so what we do in this case is we take some blocks, say a 3x3 block in this image, and we take all the pixels in this block, and we can sort of form these into a big vector. And this vector, I should actually write it like this, just for the sake of it. This vector actually becomes the first row in our X matrix. All right, so all these pixels here, let me kind of store this a little bit, write this a little bit more explicitly. So I'm going to have X. It's going to be a bunch of rows. I guess I don't need these brackets anymore. This group of pixels here, we take those, we do flatten those. So we just concatenate all of those together, and those things become the first row in this matrix. We then move to the next group of 3 pixels. I think I made my image 7x7, unfortunately. Ignore that last column in the image. And make that group the second row in our image. And then similarly, this pixel here might be, or this group of pixels, this patch, might be the third row, and this last group might be the fourth row. Right. Of course, this is a very simple sort of patching of this image, and I realize this looks messy, but hopefully in constructing it, you sort of see what's happening here. We're taking each kind of grouping of pixels in some patch size. It doesn't matter what the patch size is. It could be a 4x4 patch or a 8x8 patch. We're taking some grouping of pixels, flattening those out, and if there's a color dimension, we sort of flatten that as well, and represent that as a row in our image. Now, in the extreme case, our patch size is just sort of 1, and we've actually recovered kind of the original unstructured representation of our model. But as long as we have some patch size, this actually captures this fact that these pixels are somehow spatially close together, and therefore this element in our matrix kind of represents those spatially close together items. And this is actually the representation that people use when talking about things like image transformers and modern image models, but they also work with things like convolutional networks as well. So just to be clear, you can have here, you could have the left multiplication it contains things typically like self-attention, which we're going to talk about next time. This is a way of mixing together different rows, but it also includes convolutions and things like this. And it's not actually not obvious how to represent convolutions kind of as left matrix multiplications, and it takes a little bit of sort of manipulation to sort of make these things work, but this is all how we do it. And then the right multiplications are just linear, as they always are, just linear or neural network layers, linear layers. And through a combination of these things, this and nonlinear elements, you get modern image models. But again, I don't want to dwell too much on this. I'm not going to give any more examples because, again, we're not going to deal with any graph models or any other sequence models and things like this. But you have things like graph models, where you represent basically the nodes of a graph. This is a graph in the computer science sense, so a collection of vertices and edges. You represent the nodes of the network, the vertices of a network as elements of X. So this is sort of elements of, or I should say, nodes in the graph. Nodes in the graph are elements of X, and then right multiplication applies linear operations to each node, applies linear operations at each node independently, and left multiplications. And if you have ever sort of seen things or done manipulation on graphs before, these are things like the adjacency matrix of the graph. The graph mixed together the different nodes. Again, we're not going to deal with graph networks at all. I just want to emphasize that graph networks also follow this exact kind of modeling choice. Finally, I'll also talk about recurrent, really, or their sort of modern incarnation, which is the state, sort of the what's what are called state space models. Here, the input represents some sequence, and these can also be applied to language models, by the way. Input represents a sequence. Usually the right multiplication is, again, just linear. Right multiplication is just linear, transforms each sequence element. I'm going to run out of space here. Transforms each element. And left multiplies, so left multiplications, which could be things like in recurrent networks, these are called shift operators. So these sort of shift things in the sequence over by one to mix together different elements in that sequence. Shift operators. And for state space models, these actually are these are large matrices that sort of mix together multiple past elements in the sequence, or sequence mixing. These really mix together different elements in the sequence. Now, this is often not how state space models or recurrent models are framed. It's also not always how convolutional models and stuff are framed. But the thing that I want to emphasize here is that all kind of modern neural networks really can be represented, really not only can be represented this way, I would actually argue this is the right way to think about them, the right way to think about how we process graphs, how we process images, how we process other types of sequences. And so this basic setting of a structured model that has these three ingredients, right multiplications, left multiplications, and nonlinear operations, this really is the basis for all kind of modern types of neural networks that process kind of real structured inputs. And this is, in fact, kind of every neural network you really will use in practice. Okay, so with that kind of as our basic starting point, next class we are going to dive into one particular form of structured input model. And in particular, we're going to dive down to one particular type of left multiplication, i.e. one particular way of mixing together elements that's widely used throughout kind of all modern models, and that is the self-attention operator. This forms the basis for what's called a transformer architecture, which in itself is kind of the most common model for large language models. So that's coming up next time, and I'll see everyone soon.